This is lesson 3 in the capacitance topic. This is about energy that is stored on capacitors. These are the learning outcomes, and these are the spec points for the lesson. There's a few equations. One of the main reasons that capacitors are used is because they're able to store large amounts of electrical energy. And the advantage that capacitors have over batteries is they're able to then get rid of that energy very quickly, which means that you can use a flash, for example, that is powered simply by a capacitor, and the capacitor allows your flash to be very, very bright for a short period of time. And they're very useful. And to think about the amount of energy that's stored in a capacitor, we need to think about the charge that lies upon it. So let's have a look at this diagram of a capacitor. Here I've got a positive plate and a negative plate of a capacitor. This is full of electrons, this is void of electrons. There aren't many here, but there are lots here. In order for me to put some more charge onto the capacitor, so let's say I want to keep on charging the capacitor, I'm going to have to try and push that electron on. I would have to be doing work, using energy, to push that electron onto this negative plate. Because this negative plate and this negative electron will repel each other. So it's going to be difficult. I have to use energy to push that onto there. In a similar fashion, this electron over here will have to be pulled off of this positive plate. This electron has got a negative charge, this is positively charged, so it will require energy to pull that away because they will be attracted. So it requires energy to push that electron onto the negative plate, and it requires energy to pull that electron off of the positive plate. It has to be pushed, and this one has to be pulled. The more charge that this has, the more charged up the plate is, the more difficult it is to push the electrons on. And we can plot a graph of that says the more charge I have on there, the more potential difference I need, the more push I need to put more electrons onto the plate. So to increase the charge at the beginning is quite easy. To increase the charge at the beginning is quite easy. I don't need much potential difference. I don't need much pushing on the electrons because there's not much repelling them. But when the plate gets really, really charged up, like over here, it requires much higher potential differences to push the electrons onto the plate. And the area underneath the graph represents the energy that is stored on the capacitor. I'm doing work, I'm doing energy to push the electrons on, which means that the capacitor is then storing the energy. The area underneath the graph stores the energy, it tells me how much energy is stored, and because it is the shape of a triangle, we have to do half base times height. So the energy stored by a capacitor is given as a half times the charge times the potential difference. We can substitute into this equation the equation for capacitance, C equals Q over V, and we can get a few different forms of that equation. These are the three forms of the equation, where W represents the work done to put charge on the capacitor, but we're going to talk about W really meaning the energy stored by the capacitor. Q is the charge, V represents potential difference, and C represents the capacitance. Bear in mind that often when you're given capacitance, it's in microfarads, so we have to convert it, times it by 10 to the minus 6, to work out the amount of energy in joules. Let's have a go at a question with this. This is the first question in the Isaac Physics board. Here we've got a capacitor with capacitance 100 microfarads. It's got a voltage of 6 volts. We have to work out the charge stored in the capacitor. So the variables I know are the capacitance and the voltage. And then using the capacitance equation, I plug in my numbers and I get a charge of 6.0 times 10 to the minus 4 coulombs. And times 10 to the minus, you can do this to do times 10 to the power of in Isaac Physics, you can just use an E. So you would write that in. Next bit is what is the energy stored. So this is the bit for today's lesson. Well, I've got everything now. Now I've got C, V, but I've also got Q. I'm going to use the equation that just has C and V, because that was what was given to me initially. The energy equation that has just C and V in it is W equals a half V squared times C. So I'm going to have a half times 6 squared, the voltage, times the capacitance, 100 times 10 to the minus 6. And that gives me 1.8 times 10 to the minus 3. And to put that into Isaac Physics, you would do 1.8 E minus 3, where E means times 10 to the power of. So not much energy, pretty low, but it's just one small capacitance capacitor. You would expect that. Now you can do some Isaac Physics questions, which are the ones set for this week. This is an example question where we've got two capacitors and we have to work out the total energy being stored. These two are connected in series, so read the question. So it would look something like this. We've got our power supply of 24 volts and two capacitors in series, both 300 microfarads. To work out the total energy stored, we're going to consider these two capacitors as acting as sort of one single capacitor. And we're going to work out the capacitance total of the both of them. So to do that, we're going to use the equation to work out capacitance in series, which is this. And working out C, we would find out C is 150 microfarads and the voltage was 24 volts. Using this version of the energy equation, we would plug in our values and we would get 0.0432 joules. A question for you to try is a very similar question to the one we just did, but this time the two capacitors are connected in parallel. Can you work out the total energy stored in this scenario? Pause the video now, work it out, and I'll show the answer in a second. And that would be the answer.